Welcome to the lecture on energy aware software systems. So, this is a slide, possibly you may say it is a digression from the main topic of compilation, but there is a reason for it. So, let me state the motivation first and then look at the contents of the lecture. So, suppose we want to optimize energy consumption in a computer system. It is not enough if we optimize the program for the sake of energy consumption. The energy consumption in a complete computer system actually depends on almost every other subsystem, the operating system, the network interface, the memory, the cache and any other peripherals attached to it like the disk and so on and so forth. So, if you simply optimize the program and reduce the energy consumption of the CPU per se, the overall energy in the system may not be minimized. In fact, the CPU energy may be only about 25% of the total energy consumption. So, in some sense this also shows what a compiler optimization cannot really do. There is much more to it than just compiler optimization. So, to get a feel for such a limitation, it will be necessary for us to look at other things as well. So, let me go back one step. Yeah, okay. So, we are going to look at the reasons why energy aware design is important in the introduction. Then we will look at a case study on clouds and data centers to see what is the magnitude of saving that we can get and how. We also need to look at models for power and energy consumption, because the basis for any optimization either in a compiler or operating system depends on how good the model is. So, we will also consider operating system and system application level optimizations, power aware networks, energy efficiency of system models, microarchitectural techniques to save energy in the CPU, compiler techniques to save dynamic and static energy in the CPU, saving communication energy in the CPU, energy aware memory and of course, summary finally. So, let us see what exactly is energy aware design. So, any software design will be there will be a trade off, do we want to increase the performance of the software or do we want to reduce the power consumption. If you increase the speed of the CPU, the performance will go up, but the power consumption will also go up. And if you reduce the power consumption by say lowering the voltage, then the performance will also go down. So, it is very difficult to increase performance and reduce power consumption at the same time, but that is our goal finally. We want to actually provide the same level of performance for the software, but we would like to consume much less power than we used to. So, power consumption reduction, energy reduction etcetera has received a lot of attention in the last few years. For example, we have battery operated mobile systems, we want to retain the charge on the battery as long as possible, and then that is at the lower end. At the higher end, if you look at a data center, a large one say with 8,000 servers, the power consumption of this would be 2 megawatts. So, any reduction in this power will actually translate to money directly. And energy aware design does not necessarily minimize power or energy. So, let us see what it really means. For example, it is possible to decrease peak power consumption in a processor by delaying issue of some instructions to smoothen instruction issue distribution. This is a fairly well known thing. So, peak power consumption will come down, but this will increase the total power energy consumption due to the extra time needed to execute the application. Because we have delayed instructions, more time will be needed to execute the application. So, that means the chip is on for a longer duration, so more power consumption. So, this is a power aware design. In other words, we have reduced the power consumption, peak power consumption, but it is not a low power design, because it does not reduce the power consumption. So, power and energy efficiency are separate design goals. So, for example, clock rate reduction reduces the power demand, but it may increase the time and hence the energy consumption. So, why? Chip clock rate will reduce the power consumption, but the frequency being low, you need more time to execute the program. Power constrained applications and energy constrained applications are also distinct. So, we are actually clarifying terminology here. So, energy constrained applications are, for example, running on batteries. There is a finite amount of energy, we need to make the best use of it. So, we have energy constrained applications running on it. Power constrained application, for example, running on solar power, there is a finite amount of power available, because it depends on the size of the solar cells. So, you really cannot increase it without increasing the size of the solar array. To give you some examples of how to save energy, inside the CPU we can exploit the idleness of the CPU. In other words, whenever the CPU is idle, we could put in a small piece of hardware inside, which switches off parts of the CPU, say maybe the ALUs and so on, a cache. Similarly, the operating system and device drivers, they can manage power of the peripheral devices very intelligently. So, whenever the device is not being used, perhaps the power that is supplied to it can be cut off, and or the voltage can be reduced, etc., etc. So, this is seen very readily in the display of laptops and mobile phones. So, the display switches off after a few seconds, so that in the mobile, or after 10 to 15 minutes in a laptop, so that if the user is not using the laptop or mobile, there is no need to waste power on the display. Software controlled clock management for onboard peripherals and controllers. So, clock speed could be reduced or increased based on the requirement. Memory controllers manage power of memory subsystems. So, it is possible to place memory blocks in low power mode when the memory is not being used at all for a fair amount of time, and then bring it back to life with when there is a demand for the memory. So, these are a few examples of how to save energy and power inside or outside a CPU. We will see more of them as we go on. So, what exactly is system level energy aware design? So, such a design includes power and energy modeling, and it also includes management issues at microarchitecture level, compiler level, OS level, and also the networking layers of the system. So, we are looking at optimization at all levels. So, let us see what these mean with some examples. If you consider a clustered design with local clock, so in other words, there are clusters of function units, not just one function unit in the CPU. and instead of having a global clock for the several clusters, there would be a local clock for each cluster, and this is a well known design strategy. It reduces capacitance of the entire system. So, this is a microarchitecture level design consideration which can reduce power requirements, because once the capacitance decreases, the charge and discharge etc. Will be less, and power consumption will be reduced. Instruction scheduling reduces activity factor A, and this is a compiler level optimization. So, if a function unit is not used, for example, for a few cycles, based on the history of usage, the compiler actually the architecture would have switched off the function unit, and when an instruction executes again on this particular unit, it is brought to life. So, if this happens at random, then there may be a wastage of power, because switching on and switching off of the function unit requires much more power than executing something or staying idle. So, what an instruction scheduler in a compiler can do is to rearrange instructions, so that a function unit which is busy keeps on doing work, that is, it keeps on executing instructions, and a function unit which is idle actually remains as idle as long as possible. In other words, by rearranging instructions, we try to increase the busy periods and also the idle periods of function units. So, we reduce the number of transitions from high to low and low to high, thereby saving energy and power. Operating system level heuristics reduce the source voltage VDD and the frequency of when peak performance is not needed. So, if there are programs running on the system, and the operating system a priori knows that a particular program can run slowly, there is no hurry for it to complete. When the program is running, when that particular program is running, the operating system can reduce the source voltage and the frequency of the chip, and thereby reducing the energy consumption. The network layer puts network interface in standby mode when it is not likely to receive any message. So, thereby again there is obvious saving of power. So, let us consider the effect of shrinking device size on energy aware design. Why should we do that? The point is, with each generational scaling of feature size, more complex and aggressive designs are being used. That is, we all know that the integrated circuits when they were introduced in 70s had only a few gates on them, and slowly gradually now they have billions of gates and transistors on them. This is possible only because there is a reduction in the size of each one of these devices. So, there is more area available on the chip. So, more complex and aggressive designs are now being used. So, these designs employ higher clock frequencies, they use larger chip area and a much larger number of transistors. So, for the alpha processor and the generations of them really, let us see how the power utilization is. So, for the 21064, the frequency was 200 megahertz, die size was 234 millimeter square, power consumption was 30 watts and the power supply was 3.3 volts. Then, as the next generation of these devices were introduced, the size of the die reduced, it actually increased, the supply, for example, from 234 it became 299, 313, 340, 396, etc. So, the devices became more and more complex, but the frequency also increased 300, 575, 1000, 2000, etc. See that the supply voltage really reduced 3.3, 2.2, 1.5 and 21464 uses 1.2 volts, die size is 396, frequency is 2000 megahertz, 2 gigahertz, but the power consumption is a 150 watt consumption. So, power consumption, even though the device size has reduced, has increased because the number of devices has really gone up by leaps and bounds. So, the size of the chip and the number of devices being large results in higher power dissipation. So, that means shrinking device size does not imply less power dissipation as one may think. Let us also look at the power density on chips. So, this is a slightly old graph, but it suffices to give us the information that we require. So, starting from 386 here, okay, as we went to 486, Pentium, Pentium Pro, etc., and to Pentium 4. There is a steady increase in the power density. So, right, watt per centimeter square is on this side. So, there has been a steady increase. So, Pentium 4 okay, is at some level, and you can see that the next bar corresponds to a nuclear reactor. In other words, Pentium 4 is only slightly lower in power density, or it is only slightly less hot compared to the inside of a power nuclear reactor, and after the nuclear reactor would be actually the sun. Okay. So, at the Pentium 4 level, there is already probably the maximum or just below the maximum, as far as we have reached that maximum as far as the power density is concerned, and this is the reason why multi-core chips have been introduced. So, if you look at the multi-core chip specification carefully, you will see that the frequency of each core is lower and the number of cores per processor is more than 1. So, what really has happened is you have reduced the power density, frequency being lower, the power consumption will also be lower. So, power density on the chips has reduced, but to make up for the loss of performance, the number of cores has been increased. So, that if the software programmers are smart enough, they actually give you the same performance. But increasing the power density in chips decreases reliability and lifetimes of chips, it decreases battery life, it increases power production cost due to complex cooling and packaging, it affects environment and the human body. Power density ultimately precludes further scaling of CMOS chips. I already mentioned this. What are the various techniques available at various levels to achieve energy savings? So, at the lowest level we have transistors, gates, architecture, and then the software layer is above that. So, operating systems, compiler, virtual machine, applications. At the various levels, let us take a look at the techniques which are used. At the transistor level, the size of the transistors and the transistor ordering actually controls the energy consumption. At the gate level, technology mapping, which particular technology, and the gate restructuring control energy consumption. At the architecture level, clock, memory and interconnect optimizations, which we are going to see later, will control power consumption and energy consumption. And then with applications, virtual machines, compilers and operating systems, we have a host of techniques which interact with each other. That is the reason why there is no separation between these techniques. So, we can do better algorithm design. We could actually put resources such as function units into hibernation, then we could actually run image processing programs which give you coarser images and thereby save power. We could do remote execution, do not execute on the mobile unit, but send the application to rather execute the application on a remote server. Then scheduling of instructions, which I already mentioned, memory management, turning off cache and memory banks at when no performance is needed, and energy accounting. So, if we will see in detail when we actually look at the cloud and the data center application. So, in other words, we really need to look at all aspects of a computer system, starting from hardware to software to application, in order to reduce the power consumption. Where does the power go? Which parts of a system consume more or less power? Let us see, and what type of a system, of course. At the bottom of this chart, we have very low power devices such as sensors, and then there are 4 columns corresponding to storage, communication and I/O, computation and others. So, a sensor network system will have very little storage. So, it is not very important to have more storage, and then so this could be 2. For example, there is not too much storage on a low power sensor system, okay. But if it is a non RF device, there could be a lot of storage. So, that is why it is 2 for sensor devices, and non RF hardware it is 1, that is most important to consume power. Communication is the highest power consumption apparatus on the sensor, the transmitter and receiver, whereas computation is least important. So, it does not take too much power to compute whatever it is read. Whereas, at the highest end, the server, the DRAM and disk, they are the storage devices, and it is important to conserve power in these devices. Communication, of course, is not so important in a server. Computation is very important. So, we need to have the CPU reduce power consumption, and of course, power supplies also need to be designed appropriately to reduce the power consumption. So, this is how the power consumption spectrum really looks like. So, in a workstation, for example, rather in a system on chip, etc., storage is very high. So, we need to very low. So, we need to conserve power only in the communication, whereas if you look at no communication digital device, there may be a lot of storage. So, we need to reduce the power consumption in storage, etc. So, the application and the device actually are important to see which one deserves attention for power consumption reduction. So, let us take a simple case study of clouds and data centers. So, clouds are nothing but for us the abstraction is it is a collection of computing systems, extraordinarily large warehouse sized computing systems. So, clouds and data centers are the same as far as we are concerned. There is a technical difference between the two, but that is not important for us. So, these are extraordinarily large, they would have possibly 4 to 8,000 servers or more. The cost of building data center facilities is very large. In fact, apart from the computing elements, we need to actually worry a lot about the power capacity provisioning as well. How much power capacity should we provide for a data center? So, power capacity provisioning can be as expensive as recurring energy consumption costs. So, we need to build generator, UPS stations and so on and so forth, and this becomes very important. So, what happens is you could actually be providing a large capacity, but we may not be using all the capacity. So, you have wasted a lot of money in building the power plant and so on, with a capacity which is more than what is needed. But if you provide very little expansion possibility, then you may be actually getting saturated very soon, and you will not be able to add more servers and more equipment to your data center. So, there are strong economic incentives to operate facilities close to the maximum, because if you operate the power plant etcetera at the almost the maximum level, non-recurring costs can be amortized. So, you can recover the non-recurring costs very quickly. So, in this study we do not consider power conversion losses and power for cooling, that is air conditioning etcetera. So, maintaining, but the saying yes, we must use the power plant to its maximum capacity is easy to say. So, maintaining maximum capacity operation is very hard in practice. Why? There are uncertainties in equipment power ratings. So, you may say something requires 60 watts, but actually it may be requiring only 15 to 20 watts when it is running on medium load, and it may be requiring the full 60 watt only at very peak load, which is very infrequent. So, this is the problem. So, the manufacturer would have rated the equipment as 60 watts, but in reality on the average most of the time it may be running at 20 to 30 watts with 20 to 30 watts usage. Power consumption varies with actual computing activity. This is another problem. So, computer systems do not require do not take the same amount of power continuously, their requirement varies with the application which is running. Effective power provisioning strategies are needed. Why? We need to determine how much computing equipment can be safely and efficiently hosted within a given power budget. So, putting very few computing equipment based on the nameplate rather specification plate figures, that would be risky, because you are going to put very few of them, and power the plant will not be used to its maximum capacity. Whereas, if you put too many, then there may be outages, and this will create a service level service violation, agreement violation, and this may be very expensive. So, we cannot run the business risk of exceeding the maximum capacity. So, we should be very careful and judicious in planning how many elements we can, computing elements we can put in the data center. How do we determine the right deployment, and what power management strategies are we going to use? So, this requires understanding simultaneous power usage characteristics of thousands of machines over time. So, a data center would have thousands of machines. So, it is very difficult and almost impossible to learn the characteristics of every machine. Well, in some machine may fail and it may be replaced as well. So, it becomes almost impossible to know the exact characteristics, power usage characteristics of all the machines. What are the important factors that we need to keep in mind? The rated maximum power of computing equipment is overly conservative and not useful. I already mentioned this. So, whatever is mentioned on the plate outside the equipment is an overrating. So, we can't use this for counting the number of equipment. Actual consumed power of servers varies significantly with activity. So, applications determine this amount, and different applications exercise large scale systems differently. So, this is another issue. Hence, we need to monitor large scale workloads, and only then we can get insights into aggregate load at the data center level. So, unless large scale workloads are monitored, it's you cannot really get ideas on how to control the power consumption in a system. Running small applications on a single CPU etcetera will not give us this insight. This is the data center power distribution hierarchy. So, we have a main supply, a transformer, then a switch which either switches to the main supply or to the generator. Then we have a number of UPS, then we have static transfer switches to switch the power distribution unit to either this UPS or this UPS. So, and then at the lower level is, so you observe that the highest level power capacity is 1000 kilowatts. As we go down to the power distribution unit, each one of them can handle 200 kilowatts. The PDU supplies panels, each of which can handle 50 kilowatts. Panels in turn supply to racks, each of which can handle 2.5 kilowatts, and the racks will contain the motherboards. So, each of which may require 300 to 500 or more watts. So, inefficient use of power budget is a problem. So, we may have staged deployment, in other words facility is sized to accommodate business demand growth. So, we do not use the entire power plant, we add only a few units, and as power our requirement goes up, we really put more and more units into operation. Fragmentation. So, addition of one more unit might exceed the levels limit. For example, at the rack level, you may not be able to add one more board, because the rack capacity of 2.5 kilowatt may get exceeded. That is the by looking at the specifications of that motherboard. But in reality, each motherboard may be taking quite a bit less compared to what is the specification. So, there is unused capacity even at the rack level. So, for example, you have put 5 boards, there may be possibility of putting 6 or maybe 7 boards. So, that means a little bit of power capacity has not been used at the rack level, and similarly at each rack level this can accumulate, then at the PDU level it becomes bigger, and finally, there may be a lot of capacity in the system which is unutilized, but fragmented up to the rack level. There is the conservative equipment rating which I mentioned already, it is actually 60% more than what is really used. Variable load and statistical effects. For example, statistically it is known that large groups are, it is unlikely that large groups of systems will be at their peak activity levels as the size of the group increases. So, in other words, if there are thousands of processors, not all 1000 processors will run at the peak capacity level. So, how do we estimate power? So, we measure the CPU usage using performance counters, and the total system power, that is using some meters and so on, and find a curve that approximates system power against CPU usage. So, what we want to tie is the CPU usage to the total system power, and this is necessary for power capping, which I will explain little later. So, in other words, we want to actually measure only the CPU usage, which is very easy to do by software using performance counters. And once we have a graph and an equation which tells you for each CPU usage what is the system power, it can be used to our advantage. We do not have to measure system power all the time. Here is the graph. So, this is the idle power level and this is the busy power level for the system. In between, the power utilization of the system actually varies. So, these bars, vertical bars as we see are the actual measurements that we have taken, and in between we have a line here at the lower level we have a dotted line, and in the middle of these bars we have a solid line, right. So, the solid line and the dotted line correspond to two models which have been fitted to this particular usage pattern. So, this has CPU utilization on this end and system power consumption on the other side. So, one of the models the solid line model seems very accurate. It is actually reflects how the power is consumed within the system. So, let us see whether this tallies with the actual system and measurements. So, here are two graphs. One of them is the measured power consumption in the system, and the other is the estimated power consumption in the system using the fitted model, that is the equation that we saw in the previous slide. So, you can see that the measured power consumption is higher than the estimated one, but only by a fixed offset. So, that offset is the same at all points in time. So, that can be easily adjusted. So, the moral of the story is by using that equation which we presented in the last slide, we are able to actually come up with a very accurate estimate of the power consumed by the whole system as a function of the CPU usage. Let us also see how much power is used on the average in a system when running applications. So, on this x axis we have normalized power consumption, and on the y axis we have cumulative distribution of time. Okay. So, what is the implication? How do we read this these graphs? At the lowest level, when we are yet to begin, that is we are just idling, the normalized power consumption is still about 0.5 or so. In other words, this is the idle power consumption of the system when the system is doing nothing. And as we go on executing the program, we will reach 1, that is the end. Okay. And during this transition from 0 to 1, that is we actually see that the power consumption of the various applications, web search, web mail, map reduce, etc., they vary. So, let us look at a mix of these applications. So, we start with 0.65 as idle power consumption, and 60% of the time actually, okay, we would be using only about 0.72 or 72% of the peak power consumption of the system. And even when we reach 1, that is let us assume that there are portions of the program which actually execute at the peak power. This is the peak power anyway. The peak power is still only 85% of the maximum power that we assumed we have. Okay. So, the rating actually is 1, but what we have used is 85%. So, for most of the time the applications say 95% of the time the applications run really at less than 80% peak capacity. So, 20% is the over provisioning that we have on the computer system. So, in other words, we could actually put maybe more programs on it. So, the CPU can be rather sorry, we could put another CPU, so that one more program can be run on that particular CPU, and the power consumption if we add 1:4 or something like that, 20% saving in each one of them will give us one more CPU which can be added. So, this is the way we actually use this graph to determine whether we are operating, we should add something or we should not add something. For example, when should we not add something? So, consider this particular graph. Okay. So, this really corresponds to web search. So, web search, there are parts of the program when the power consumption in the system is almost 95%. So, in other words, you cannot take the risk of adding another CPU if only web search is running on all the machines. Okay. So, if there is a mix of these programs, then maybe for 4 CPUs you could add an extra CPU, etc., etc. This is a similar graph. So, normalized power with rack, PDU and cluster level for various applications mix. So, if you look at it, this is the cluster level, So, see that cluster level is over provisioned 30% more, it really consumes only 72% most of even at the highest level. Okay. So, there are no parts of no programs which really require it to consume 100% of the power that is possible. So, now having said all this, we understand that when the CPU runs programs, the data center runs programs of all kinds. Not all CPUs are going to run at the highest peak level, peak power level, and therefore, there is actually a possibility of adding more CPUs and run more programs. Okay. So, power is saved because each CPU requires less power than what its rating says, maybe 70% is all that it is using, 30% is spare. So, we could add one for extra CPU for each of the 3 CPUs that is in the system. But suppose we add more CPUs and suddenly the processors start executing programs which require high power consumption, that is possible, right. In such a case, we could be exceeding the power consumption of the system beyond the rating. So, the system is under provision most of the time. Most processors can be added, more processors can be added whenever maximum power is not used, but then loads can be monitored, and whenever power utilization tends to go beyond a cap, that is whatever threshold we set is called the cap, tasks can be descheduled or dynamic voltage scaling can be deployed. So, in other words, you reduce the voltage of the entire data center, all CPUs. So, that will reduce the power consumption of all the CPUs, and you can work at a lower frequency and lower performance level for a certain duration. Once some of the tasks complete and exit, perhaps the situation will change and you can increase the voltage and the frequency of the system again. So, this works well with loose service level guarantees. So, there are no hard service level guarantees, that is I am going to finish this particular job in such and such an amount of time, so much time. So, such guarantees are not really provided. So, give or take an hour, if your program runs to completion, the customer is happy. About 45% increase in machine deployment with just 1% of time spent in power capping mode. So, in other words, the system actually starts using peak or little more than peak power only for 1% of the time. Then in that 1% of the time you reduce the voltage and immediately the system finishes some jobs and goes back to low power or underutilized mode again. This is really what happens in practice. So, because of that we can actually increase 45, we have really put 45% more CPUs and still only 1% of the time the machine has gone to peak power condition. So, only 1% of the time is spent in power capping mode, that is when the peak power condition is met, and number of trips beyond the cap is only 9 per month, only 9 times, and average length of each trip is only 48 minutes. So, if you have a loose service level agreement, this is hardly the price to pay, because you are using the power provisioning of the plant to its maximum capacity. So, the customer is also going to be charged less, you are going to have more customers. So, the cost per customer will be lesser. So, what is the impact of dynamic voltage scaling on energy saving at the data center level? I already mentioned that we are going to use DVS at the data center level. So, what we really have are 4 sets of graphs for different application, 3 of them for different applications, and on a real data center with a mix of applications. This is for the 4th one. And we have 3 bars in each of these groups. One says 5%, the next one says 20% and 50% CPU utilization threshold. What does this really mean? So, on this side we have energy saving. So, we can 5% means I cannot tolerate very slow CPU performance, So, if my at some point in time, let us say I have reduced the voltage, okay, dynamic voltage scaling has happened, I have reduced the voltage of the data center. Now, the CPU utilization has come down by 5% because of this, then I cannot tolerate anymore, I am going to increase the voltage back to its normal. So, even this obviously, if this threshold is only 5%, then I will be running the data center at most of the time at the highest voltage level, and only a very small number of times am I really going to reduce the voltage. So, the saving is quite less, it could is about 8 to 10%, whereas if I can tolerate 20% slowdown in my CPU speed, in other words my application takes 20% more time, then I get more, maybe 15% or so, and if I can tolerate 50% slowdown in my application, I can actually get much more saving, 20% or more. But obviously, we cannot sacrifice performance to such a great extent. So, we may be somewhere between 5 and 20% as far as DVS is concerned. Normally, it is not more than 5-6%. Okay. So, but later we will also be seeing compiler techniques to do dynamic voltage scaling. So, then we can do fine grained control actually, and get much more power saving than what is mentioned here. This is actually at the data center level, the operating system itself would reduce the voltage of the entire data center and not on a per CPU basis. So, now we consider power and energy models. So, the first part we considered the introduction, and then we saw cloud and data center application power saving. So, why do we need power and energy models? So, we need power energy models during early design space exploration for power estimation. So, we have started designing a system, and we need to know how much power our system is going to consume when it is implemented. Why? Why do we need such an estimate? Well, we want to actually look at alternative designs which can save energy. So, unless we know how much power each one of these designs will take, we really cannot decide on which design to implement. At this level, the models may not be very accurate, because we do not have all the data about the implementation, but they address relative power efficiency. So, is design A better than design B? That is going to be the question that we answer. So, this can be answered reasonably well with the power and energy models that we are going to study. They are also required to perform optimizations in compilers and the operating system. Compilers and OS require models to estimate power and energy consumption, and thereby they use strategy A, B, C, etc., in order to save the energy. So, OS and compilers also require such models. Let us look at the first model, instruction and function level power models. So, at the instruction level, we are going to assign a power cost to each assembly instruction class. So, in other words, the entire set of ALU instructions, add, subtract, etc., will all be, each of these will be assigned the same cost. Okay. So, each class of instructions which uses the ALU or the floating point unit or the memory or something else will be assigned a cost. So, each instruction in that class will be assumed to take the to consume the same amount of power. Then how do we assign this cost? We experimentally measure current drawn by a processor while executing a known sequence of instructions. So, we try to put known sequence, the same kind of instructions, execute, make the program run on a processor, then look at the current which is drawn by the processor, and then compute the power by multiplying it by the voltage. Then such a simple scheme has problems. There are many inter instruction effects. For example, cache hit miss. So, if the data or the instruction is in a cache, then the power consumption is different compared to when it is in main memory and not in the cache. Then there could be pipeline interlocks. So, if there is a delay and the load is not yet over, there is a pipeline stall. So, this could actually cause a different power dissipation in the system. So, to take care of such inter instruction effects, we really have to run a very large number of programs in order to assign cost to the instruction. And the problem is there are a large number of such inter instruction effects. So, the multiplicative effect would be large, and we will have to analyze collect and analyze extremely large number of instruction traces in order to assign reasonable cost to the instructions. So, this model is not very easy to let us say make and calibrate. Suppose we want to do it on a program level or function level. Okay. So, we can have macro models characterizing the average energy consumption of a function or a group of functions. For example, suppose we know that we are running insertion sort, right. Then we know that the time required for insertion sort is O n square, where n is the number of elements. So, we could choose a quadratic power model for the power consumption also, say a n square plus b n plus c for the insertion sort program, measure the actual power dissipation for different values of n, and then use regression analysis to find ABC. So, then we have given n, we can say what is the power consumption for that particular n. So, this is a way of characterizing the energy consumption of a program. Such high level models allow designers to assess a number of candidate architectures and alternative software implementations. So, I know in an embedded system that the same program or same set of programs will be run again and again. So, in a washing machine the same program runs again and again, right, or in a media player also say the same thing. So, the program is known, and if we build the approximate models like what we saw just now for this particular program on various architectures, then we can assess and say okay, this architecture is better for this program, or this architecture is very bad for this particular program, etc. And then we can also look at alternative software implementation. Insertion sort may be written in different ways, and you can similarly compute rather have a model for each one of these implementations, test it on various architectures and choose the correct candidate architecture for your application. However, for very detailed analysis and design, that is design of the hardware, power and energy models of main subsystems and components are also needed. In other words, we will need microarchitecture level, ALU level, memory level, cache level, interconnection level models in order to study the design and then make an estimate of how much power is consumed by that particular design. So, we will stop at this point and continue with such microarchitectural models in the next lecture. Thank you.